Till now, we have seen that in the Fermi theory of beta decay, you have seen that beta decay results from an interaction of the nucleus with the beta neutrino field. Actually, the action of the nucleus on the field is to create the electron and the neutron. We also know that the beta decay process is a weak interaction, and the beta transition takes place under certain quantum conditions. Actually, the quantum numbers which govern such transitions are generally two quantum numbers. The first one is actually called total angular momentum or spin of the nucleus, that is I, and the another important quantum number which decides the state is actually parity. So these are the two quantum numbers which actually determines, or you can say which actually govern the transitions like beta decay. Okay. In fact, owing to the isotropy of space, these two quantum numbers are the characteristic of the state of any isolated system. Now, the first quantum number, which is called a spin of the nucleus, you know this spin means just the total angular momentum. So don't confuse with total angular momentum and a spin. You know, a spin means total angular momentum. And you have definitely an idea of parity because I have discussed this parity before this lecture. I am just giving a short meaning of this parity. You know, parity is defined as the property that the wave function psi changes sign or not when the space coordinate x, y, z are transformed by inversion to minus x minus y minus z. It means if the space coordinates x, y, z becomes minus x minus y minus z, then the sign of the wave function psi is getting changed or not. In fact, when after the inversion of the sign of these space coordinates x, y, z, the wave function changes its sign, then parity of the state is called a negative or odd parity. And when after the inversion of sign of these space coordinates x, y, z, the sign of the wave function remains same, it does not change, then the parity of the state is called even or positive, you know. So actually I have mentioned it here. You can see that if psi of minus x minus y minus z, that is equal to psi of x, y, z, it means the sign is not changing here, then the parity is even or positive. And this parity is just denoted by writing the plus sign over the as a superscript on the total angular momentum or spin of the nucleus. Okay. And if you see that psi of minus x minus y minus z becomes minus psi of x, y, z, then you call that the parity is odd or negative. Okay. In fact, you have seen that in developing the Fermi theory of beta decay, we have used the term matrix element M. And this matrix element M, which governs the actually interaction. It means what type of interaction will take place, that is decided on the basis of the matrix element. In fact, of the various possible forms of matrix element M, the one of the simplest form, which is also called the scalar form of the matrix element, and that scalar form is defined like this. This is actually the scalar form of matrix element. A scalar form. Okay, and this scalar form is defined by this equation, m equal to integral psi f star psi I d tau. Here actually psi I represents the wave function for the initial state, that is you can say the neutron state, and this psi f star is actually the complex conjugate of psi f, and psi f is the state function or wave function of the final state, that is the particle obtained after the beta decay. If neutron is converted into proton, then this psi I represents the wave function of neutron and psi f represents the wave function of proton. You know it. You have seen in the theory of beta decay proposed by Fermi, which I have already discussed in the previous lecture. In fact, this scalar form of matrix element which I have just defined, actually this form of matrix elements gives a particular selection rule for the allowed transition. And what selection rule we obtain from this scalar form of matrix element, I have mentioned it here. You can see that this matrix element gives that the selection rule like this: I equal to I prime, or you can say delta I equal to 0. Actually, this I represents the spin or the total angular momentum in initial state, and I prime represents the spin or total angular momentum in the final state. So if the after the transformation initial state is changed into the final state, then what will be the change of spin? Change of spin, that is key. This delta I means I prime minus I, and this selection rule, this matrix element gives that during the allowed beta decay transition, this delta I should be equal to 0. Okay, and parity no. Here actually this no means no change in parity. No change in parity. Actually this selection rule which I have mentioned here, that I equal to I prime or delta I equal to 0 and parity is no, this is actually known as Fermi transition, or you may also say that this is F selection rule. F for Fermi. It is called Fermi selection rule, or you can say that this is Fermi transition. So Fermi transition is obtained from this scalar form of matrix element which have been defined here, and what is that selection rule? Just this is a very simple selection rule, that during this transition, that is during the according to Fermi transition, only those transition will be allowed for which the change in total angular momentum or change in spin is equal to 0. Okay, and there will be no change in parity. It means parity will remain conserved. Okay. Now the another form of the matrix element which is actually called the tensor form, and that tensor form of the matrix element gives another selection rule, and that selection rule is called Gamow Teller selection rule. In brief, you can say that this is GT selection rule. And this GT selection rule, as I have told you, that it is found by another form of matrix element which is actually a tensorial form, and that matrix element is defined like this: m equal to integral psi f star sigma psi I d tau. Actually here this sigma is just interaction operator, or you can say that this is the generalization of Pauli's spin matrices. Okay, And when the matrix element has this tensorial form, in fact, from this form of matrix element, we obtain a set of selection rules, and that selection rule is called Gamow Teller selection rule. And what are actually those selection rules which have been which are obtained from this form of the matrix element? I have mentioned it here. You can see. In fact, these selection rules are that I prime, it means the total angular momentum or spin of the final state. This should be equal to I plus 1. It means the spin of the initial state plus 1. Or it should be equal to I, or it should be equal to I minus 1. It means if you are talking about delta I, where delta I means what? This is I prime minus I. So this delta I, which is I prime minus I, should be what? When you will subtract I from I plus 1, you will get 1. And when you will subtract I from this I, you will get 0. And when you will subtract I from I minus 1, then you will get minus 1. So according to this GT selection rule, only those transitions will be allowed in case of which the change in spin is either 1 or 0 or minus 1. You can see it here. Only these transitions will be allowed. And at the same time, there should be no change in parity. Change in spin should be either 1 or 0 or minus 1, and parity should not change. It means the parity of the initial state and the final state should be same. It means if the parity of initial state is positive, definitely the parity of final state should be positive. Only then this transition will be allowed. But one thing you should remember here, that if I is equal to 0, it means the spin of the initial state is 0, and you consider that there is a transition from I equal to 0 state to I prime equal to 0 state. It means both of these spin quantum number is same, and that is equal to 0, particularly 0. Then delta I will be 0, because 0 minus 0 will be 0. But this transition, when transition takes place from 0 spin state to another 0 spin state, then delta I will be 0, that is change in spin will be equal to 0, and this transition is allowed by the F selection rule. But remember, this transition is not allowed for the Gamow Teller selection rule. Although you have seen that the change in spin is may be equal to 0 for this GT selection rule, but this is just an exception, that it means the final state's spin and the initial state's spin must not be equal to 0. Only then the transition will be allowed. So 0 to 0 state of spin transition is not allowed. It is forbidden by the GT selection rules. Now actually we will clarify these selection rules by taking some proper examples. Now see some proper examples. First of all, you can see here that experiment shows that allowed transitions of the type delta I equal to 1. You can see delta I equal to 1 are the allowed transition for the GT selection rule, not for the F selection rule. According to F selection rule, only those transitions will be allowed for which delta I equal to 0. So if delta I is equal to 1, then such transition will be allowed by the Gamow Teller selection rule, not by the F selection rule. Okay. So you can see I have mentioned it here that experiment shows that the allowed transitions of the type delta I equal to 1 obeying GT selection rule are forbidden by the F selection rule. It is not allowed for the F selection rule. Okay. Now these are some important proper examples of such transitions. You can see here. This is just a decay of 2He4 nucleus into 3Li6 nucleus. Sorry, 2He6 nucleus into 3Li6 nucleus. And in this process, the beta particle and the antineutrino are created and emitted. Now see it here that actually this 2He6 has closed cells, you can see, and this has in fact even number of the nucleons. So all the nucleons will be paired. And if all the nucleons are paired, its total spin will be equal to 0. Okay. So what is the spin of 2He6? Its spin is 0. And what this plus sign indicates here? This plus sign actually indicates that the parity of this nucleus 2He6 is positive or even. Okay. Now again see the 3Li6. It has also the number of nucleon 6 which are actually paired. So the spin of this 3Li6 will be also 0. Okay. But spin of this beta particle is 1 by 2. And this spin of this antineutrino is also 1 by 2. And so the total spin will be 1. Okay. So in this transition, actually there is a change, or there is a transformation or transition of I equal to 0 state to what? I equal to 1 state. So what will be actually the value of delta I in this case? You can see this will be 1 minus 0, that is 1. And you know when delta I is equal to 1, that transition is allowed on the basis of GT selection rule. Okay. Now I will explain just the another example. Now see here. The another example is, you can see, the another example is what? You can see this is 6C14 and that has been converted into 7N14, and again the negative beta particle and antineutrino are created and emitted. By the same reasoning, you can see this C has 14 nucleons. So 14 is an even number, so all the nucleons are paired, and if all the nucleons are paired, the total spin or angular momentum is 0. Okay. So the initial state has I equal to 0. Now what is the value of the spin of the final state? You can see. Now the resulting daughter nucleus is what? This is 7N14. Again, the number of nucleon is 14, so all these nucleons will be paired and the spin will be 0. And again, you can see the spin of this beta particle will be what? This is 1 by 2. So this is 1 by 2 and 1 by 2, and after adding you will get 1. Okay. And again, this plus sign indicates that the parity is even. So This is also an allowed transition according to the GT selection rule, but not allowed according to the F selection rule. Because according to F selection rule, delta I should be equal to 0. But here, delta I, you can see this will be simply equal to 1 minus 0, that is 1. And now see this third example. This is just a beta emission process from the parent nucleus 32Ge75. This is germanium. And you can see here mass number is 75. So out of these 75 nucleons, 74 will be paired. 74 is paired. And only one nucleon will remain unpaired, and a spin of that only one nucleon, that will be equal to 1 by 2. So I is equal to 1 by 2. You can see it here. I is equal to 1 by 2. And again, in the daughter nucleus AS, the mass number is 75. That is, the total number of nucleons is 75. So in this case, again 74 will be paired and only one unpaired nucleon remains, and that constitute actually the spin, unpaired nucleon. And so what will be I prime? Now calculate it. The spin of unpaired nucleon of this AS is 1 by 2. Again the spin of beta is 1 by 2. Again the spin of nu bar, that is antineutrino, is 1 by 2. So this spin is 3 by 2. So I prime is 3 by 2 and I is 1 by 2. So what will be delta I? You can see this will be 3 by 2 minus 1 by 2, and that will be equal to 1. Okay. So this is also an allowed transition by the GT selection rule, but not allowed on the basis of F selection rule. I hope you have understand how we can say that such transitions are allowed obeying the GT selection rule, but they are forbidden on the basis of F selection rule. Okay. Now see the another example. In fact, it is seen that there are allowed transitions of the type 0 to 0. It means I equal to 0 and I prime also equal to 0 by the F selection rule, but forbidden by the GT selection rule. I have just mentioned this fact here too. You can see this is the same fact which I have just earlier mentioned. So it is seen that there are allowed transitions of this type, that I equal to 0 to I prime equal to 0. Such transition is actually allowed by the F selection rule, but this type of transition is not allowed by the GT selection rule. Now let us see some of the important examples for it. You can see it here. Now the parent nucleus here is 8O14. Okay, and when the positron emission or beta positive emission takes place, then the daughter nucleus is 7n star 14 plus beta plus neutrino. See here, n star, this sign of star over n represents that the daughter nucleus has been actually obtained here in some excited state. This daughter nucleus is not in its ground state, but it is in excited state. So this sign of a star represents that the daughter nucleus is in excited state. Actually, you can see that this O has 14 nucleons, so all nucleons are paired, and if they are paired, the angular momentum or the spin of the parent nucleus is equal to 0. And one thing here you should remember, that the spin of this n star nucleus is also equal to 0. Also equal to 0. Okay? And but one thing is very important here, that actually if a nucleus of 7 and 14 is not in its excited state but it is in the ground state, then its spin is not 0 but its spin is equal to 1. In ground state its spin is 1, but in excited state of this much energy, 2.31 mega electron volt energy, then its spin is equal to 0. Okay? Now, a spin of this beta plus is 1 by 2, and the spin of this neutrino is minus 1 by 2, and so this will be equal to 0. Okay? So this is just a transition from 0 to 0, which is allowed by the F selection rule but not allowed by the GT selection rule. And again, this plus sign here refers that the parity of the parent nucleus, that is parity of the initial state, is positive, and the parity of the final state is also positive. So there is no change in parity. Okay? And you can see the similar examples like this. This is 13Al26 that is transformed into the daughter nucleus 12Mg26, and at the same time positron and neutrino are emitted. And again you can check that the transition is in fact 0 plus to 0 plus, and similarly in this case 17Cl34, this transition is allowed by F selection rule because this is also a transition from I equal to 0 to I prime equal to 0. And in all cases you can see that parity has been not changed, because in the initial state parity is positive, and in the final state again you can see that parity is positive. Okay? Now we'll see the third important example. In fact, in third example is actually different from the first and second. In fact, in this case we will see that there are transitions which are allowed by both selection rules. Both selection rules allow those transitions. In fact, this is always possible in the allowed decays in which I prime is equal to IF but not equal to 0. It means both selection rules actually allow any transition only when the spin of initial state and the spin of final state are same, but that is not equal to 0. It means I equal to IF, but II and IF should have some non-zero value. Then such transitions will be allowed by F selection rule and also by GT selection rule. Now see the proper example for this. See here. Here just a neutron has been converted into a proton and beta minus and antineutrino. You can see the spin of this neutron is 1 by 2 and its parity is positive, so this has been written as 1 by 2 plus. And what will be actually the parity of the final state? You can check it. Not parity, but in fact angular momentum. I prime is what? In fact, the spin of this proton will be 1 by 2, and that of the beta particle is also 1 by 2, and that of the antineutrino it is minus 1 by 2. So these two will cancel out, and again the spin of the final state is 1 by 2 and its parity is again positive. So this is a transition from 1 by 2 plus state to 1 by 2 plus state. And what will be delta I? delta I will be equal to 0. And you know, if delta I is equal to 0, F selection rule also permits, also allows such transition, and GT selection rule also allows such transition. You can see it here. I have mentioned the selection rule earlier. You can see that delta I equal to 0 is allowed for the F selection rule, and at the same time there should be no change in parity, and this delta I equal to 0 is also allowed in case of the GT selection rule, and at the same time the parity should not change. The page has been turned. This will be just okay. You can see it here that delta I equal to 0 and no change in parity, such transition is also allowed by the GT selection rule. So as I have told you that we are seeing just some of the transitions which are allowed by both of the transition rules. Okay, and similarly you can see the another example which is of 1H3 which converts into 2He3, and again beta minus and antineutrino, and same will be the situation. You can see in 1H3 there are 3 nucleons, and so 2 will be paired and 1 will be unpaired, and spin is due to the unpaired nucleon. So I will be what? I will be equal to 1/2. Okay. Now find I prime in this example. You can see 2He3. Again there will be 1 nucleon unpaired. So the I prime will be 1/2, and for beta this is again 1/2, for antineutrino minus 1/2, and so this is again 1/2. So I and I prime both are 1/2. And similarly you can see here that in this case 16s35. 16s35. In fact, in this case, the spin will be not 1/2, but this will be in fact 3/2. Why 3/2? Because the nucleon will be not in fact in the S subcell, but it will be in the T subcell, and so in this case the initial state spin is 3/2, and similarly you can calculate that the final state 16 32 sorry, see here, since there are 16 proton and 35 is the mass number, so there are 3 unpaired nucleon. Yes, 3, and so there are 3 unpaired in fact nucleon, and so there will be the spin of the initial state in this case will be equal to 3/2. You can see. And similarly in this case the spin of the final state will be also 3/2, because in this case there are again 35 nucleon in Cl35. Okay, and and the parity in both sides you can see is positive, and so no change in fact parity. So you have seen how the selection rule permits or allows a particular transition, and how they are permitted by a particular selection rule and prohibited or forbidden by the another selection rule. Now we will see actually the forbidden transitions which are actually not allowed. We will now are going to see those transitions. In fact, we will consider what happens when the transition from initial to final nucleus does not take place by the emission of S-wave electron and the neutrino. In fact, because of the finite size of the nucleus, the electron and the neutrino emission with orbital angular momenta other than zero is also possible. And the magnitude of the wave function of electron and the beta particle, you can say psi e and psi nu, for the p wave and the d wave etc. over the nuclear volume decreases rapidly and with increasing the orbital angular momentum. In fact, in beta transitions with angular momentum carried off by the two light particles together, and so the orbital angular momentum in this case will be equal to 1, 2, 3 and so on. Okay? And when this orbital angular momentum L beta, or simply you can say L, will be 1, 2, 3 and so on, actually they are classified as first, second, third etc. forbidden state. So you can say if L is equal to 1, then it is first forbidden. L equal to 2, that will be called second forbidden. L equal to 3 will be called third forbidden. In fact, it is seen that if L is odd, in that condition, the initial and the final nuclei must have opposite parities. L is, for example, if you consider that L is equal to 1 and 1 is an odd number, in that condition, definitely the parity of the initial nucleus and the final nucleus will be just opposite. It means parity will change in these such transitions. Okay? But when L is not odd but L is even, for example, you take L equal to, let us say, 2. In that condition, the parity will not change, parity will remain same. It means that if the parity is positive for the initial nucleus, then it will be again positive for the final nucleus. Okay? In fact, in allowed transitions, the emission of leptons, that is electrons and neutrino, in the singlet state, that when you say singlet state, that is called Fermi selection rule, requires that the change in a spin, that is delta I, this should be less or equal to L beta. Okay? In case of F selection rule, delta I should be less or equal to L beta. But in the triplet state, that is in the GT selection rule, emission requires that this delta L should be in fact less or equal to L beta plus 1. L beta plus 1. Okay? So, what will be the selection rules for such transitions? You can see it here. First of all, I am just giving you the general result. Then we will talk about the particular result. You can see it here. If you are talking about the Lth forbidden, then what is the selection rule? In fact, for Lth forbidden, F selection rules are delta I should be equal to plus minus L and plus minus L minus 1. Remember. And GT selection rule for the Lth forbidden, this was delta I. Delta I should be equal to plus minus L and plus minus L plus 1. And as I have told you earlier that when L is odd, then parity changes, and when L is even, then parity does not change. Now see the proper value of this L. For example, in first forbidden, actually we will take L equal to 1. Okay? And since 1 is an odd number and you have seen that when L will be odd, then parity will change. And what is the selection rule? You have just seen that for L equal to L, delta I should be equal to plus minus L and plus minus L minus 1. So here delta I should be equal to plus minus L. L is 1, so this should be equal to plus minus 1. And again plus minus L minus 1. L is 1, 1 minus 1 will be 0. And there is no significance of sign of plus and minus before 0. So I have directly written here 0. So delta I should be equal to plus minus 1 and 0. But remember that there is an exception, that there should be not a transition from 0 to 0 state. Okay. And for GT rule, you have seen that in this case delta I should be equal to plus minus 1 and plus minus L plus 1. Since L is 1, so L plus 1 will be 2, so this is plus minus 2, and L is 1, so this is plus minus L, that is plus minus 1, and 0. And again here these are exceptions, that there should be not a transition from 0 to 0 state, 1 by 2 to 1 by 2 state, and 0 to 1 and 1 to 0. Here arrowhead is in both directions. It means neither the 0 to 1 transition and 1 to 0 transition. These are actually not neither 0 to 1 and 1 to 0 should be here. Okay. Now here is some proper example you can see for this first forbidden. Here the argon nucleus 1839 has been transformed into 19K39 and beta minus is created and emitted. Actually here there is only one unpaired nucleon, so the value of I will be equal to 1 by 2 and its parity is in fact odd, so minus sign is here. And again in this case the parity the spin of K39 will be 1 by 2, so I prime is equal to 1 by 2, and plus the spin of beta minus is also its parity is in fact 1, not parity but spin. Its spin will be 1, spin of K, and that of beta, this is equal to 1 by 2 and this is equal to 3 by 2. Okay. And the parity of the parent nucleus is in fact negative or odd, and the parity of the final state is positive. So you can see when L was actually equal to 1, in that condition the parity has been changed, minus to plus. And these are the other examples you can see and practice such example, remember it. In fact this is the case of GT selection rule, and this is the this is the F selection rule, and this is just a mixture of F and GT selection rule. Okay. Now in second forbidden L is equal to 2 and 2 is an even number, and you have seen that if L will be even, then there will be no change in parity. It means if the parity of initial state is positive, the parity of final state will be also positive. And what will be the selection rule for F selection? The rule, this will be delta I equal to plus minus L and plus minus L minus 1. The L is 2, so this is plus minus 2, and L minus 1, that will be 2 minus 1, that is 1, so this is plus minus 1. But this transition 0 to 1 and 1 to 0, this is not allowed. It means 0 to 1 and 1 to 0, this is not allowed. And for GT selection rule, you know, in case of GT selection rule, when L is equal to 2, then delta I will be equal to plus minus L plus 1. 2 plus 1 is 3, so this is plus minus 3. And again, plus minus L, this will be plus minus 2. Okay, but this transition is not allowed here. Now, these are the proper, this is a proper example here. When sodium nucleus is converted into neon, then there is just a then there is actually the angular momentum or spin of the initial state is 3, and its parity is positive, and that of the final state is 0. So this is just a transition from 3 to 0. It means the change in I will be here minus 3, 0 minus 3. Okay, and finally, as I have told you earlier and discussed, that in general you must remember that for Lth forbidden, what is the selection rule? On the basis of this general result, I have calculated the selection rule, that is F selection rule and GT selection rule for the different forbidden. Okay, so I hope you have understand the different selection rules for the allowed and the forbidden transitions. This is a very important concept. Go through the video, watch it seriously, and practice. Then you can write the answer of such problems in your examination.